The following is a presentation on avian interactions with power infrastructure. This presentation will primarily focus on bird collisions with transmission power lines. Distribution power line electrocutions will be briefly discussed, as will methods to deal with bird nesting on power lines. This presentation was created by Richard Harness, a certified wildlife biologist with EDM International, Inc. Mr. Harness has over 30 years' experience addressing avian interactions with power infrastructure. This presentation is primarily focused on understanding and addressing power line collisions with transmission power lines. Because this issue involves engineering and biological factors, background information is provided on both. An overview of a typical electrical grid is provided, along with detailed descriptions of various pieces of utility infrastructure and how they can play into collision risk. Biological factors are also addressed, along with routing considerations for new projects. Detailed informational resources for assessing the risk of avian interactions are identified, along with links. Mitigation measures are described, such as marking wires with various bird flight diverters. This includes an overview of marker installation options and typical engineering concerns. Manual and automated monitoring approaches are also covered. Transmission lines typically have adequate separation to accommodate birds, thus electrocutions are a lesser concern. Distribution lines have the potential to electrocute wildlife due to their closer spacing of conductors and grounds. Thus, some additional information on distribution electrocutions and solutions is provided. Substations will not be addressed in this module. Certain nest types can cause power reliability problems depending upon their composition, placement, and other site-specific factors. Thus, information on nest management is provided. Effectively addressing avian interactions with power lines requires biologists to understand electric utility challenges and vice versa. Important topics for capacity building are listed for both groups. Unless otherwise indicated, all photos in this presentation were taken by EDM International, Inc. The following short section describes a typical electrical system and the types of bird issues associated with each electrical component. This diagram follows power from its generation, step 1, to the end consumer, step 6. Power is first generated and then sent to a collector station. Collector station issues with birds are typically restricted to nesting issues. Power is then transmitted to load centers via transmission lines defined as 60 kilovolts or higher. Bird issues are typically limited to nesting issues and wire collisions. Transmission lines then send the power to load centers, where the voltage is stepped down at substations, where issues with birds are typically related to nesting and electrocutions on the low side of the substation. Distribution lines then come out of the substations defined as less than 60 kV. These lower voltage lines, typically in the 15 kV range, distribute power to the end consumers. Issues with birds are typically related to nesting and electrocutions. Once delivered to the consumer, transformers are used to further reduce the voltage. Issues with birds are typically related to nesting and electrocutions. Secondary feeders deliver the power to a meter and then the consumer, typically 220 volts in Asia. Issues with birds are rare due to the lower voltages. Most collisions with power lines occur with transmission lines. The following describes typical transmission components. Transmission lines can be supported by a variety of structures, usually either monopoles or lattice, as shown in this image. Insulators ensure there is no electrical path between the energized wires and the grounded structure. Conductors carry the electricity. This structure supports two circuits, one on each side. Each circuit consists of 3 dual conductor bundles with spacers. The overhead ground wire is a small uppermost wire used to intercept lightning strikes. When combined with fiber to transmit data, it is referred to as an optical ground wire. Avian collisions with power lines are a global issue. The total number of birds lost to power line collisions is unknown, but it is estimated that between 10 million and 216 million birds are killed each year in North America. Certain species are more susceptible to collisions than others. For certain species, including the imperiled great Indian bustard, collision mortality is a biologically significant source of mortality. Methods for limiting power line collisions range from proactively selecting low-risk routes in power line planning, along with selecting designs with lower risk. Reactive measures include marking and illuminating wires to make them more visible to species of concern. Research shows most collisions occur with the upper overhead ground wire, which is smaller and harder for birds to see. Research also shows most collisions occur near the center of the span, suggesting birds see the towers. The following discusses various risk components broken into 3 categories: transmission line factors, biology, and the environmental setting. This slide covers factors which may influence the number of bird collisions expected with a transmission line. Transmission line factors include configuration, number of circuits, wire diameter, the wire type and number, wire reflectance, wire sag, and wire marking. In regards to configuration, higher risk is associated with vertical configurations, which have more wire planes to cross than horizontal configurations. In terms of the number of circuits, structures with multiple circuits may increase the number of wire levels birds need to navigate, depending upon the configuration and wire sagging. Wire diameter. As previously mentioned, smaller diameter wires are harder to see, increasing risk. Wire type and number. Structures with multiple bundled wires and their associated spacers are easier to see than single primary wires. Wire reflectance. If wires are treated to reduce light reflectance, they are termed non-specular conductor. Such treated wires are harder to see. Wire sagging. If lines are parallel to each other but have different sagging, it increases the area to navigate, thus increasing risk. And last, wire marking. Wire marking makes lines more visible. Important biological factors include bird maneuverability, flight behavior, flight pattern, vision, age, sex, and health. Regarding maneuverability, birds with poor flight characteristics, such as those with high wing loading, birds with small wings relative to their body size, can have difficulty avoiding aerial obstacles. Flight behavior. Birds which regularly fly low relative to tower height increases their risk, as does flying in low light and making regular line crossings. Flight pattern. Birds flying in flocks with closely spaced birds increases the risk for trailing birds, which may not see obstacles up ahead. Vision. Birds with a wide field of vision, such as those with eyes on the side of their head, such as cranes, or birds with specialized vision for seeing underwater, may have difficulty seeing wires. Age. Young birds have less flight experience and are thus at greater risk. Sex. Birds in courtship and preoccupied and pursuit behaviors are also at greater risk. And lastly, health. Birds in poor health may have difficulty maneuvering around power lines. The power line setting also influences risk. Power line setting factors include season, habitat, land use, orientation, weather, and humans. In regards to season, bird abundance near lines may be elevated during migration, breeding, or nesting season, elevating exposure and risk to the power lines. Habitat. Power lines located near certain habitats favored by birds such as wetlands, water bodies, foraging areas, roosting and resting sites, and communal nest sites elevate exposure and risk to power lines. Land use. Power lines located near certain locations favored by birds, such as conservation areas, refuges, national parks, and important bird areas, elevate exposure and thus risk to power lines. Orientation. Power lines perpendicular to regular flight corridors place birds at greatest risk than those which are parallel. Weather. Precipitation, fog, high and variable winds, tailwinds, all make it more difficult for birds to navigate near wires. And lastly, humans. Sudden impacts made by humans may flush birds, exposing them to elevated collision risk. This image shows how various transmission line factors impact risk. For example, this structure has an overhead ground wire, single unbundled conductors, and no wire marking, all increasing collision risk. Positive factors include having the two lower wires on the same plane with similar conductor sagging. This line is also single circuit with reflective conductor, both positive factors. This image shows how various biological factors impact risk. For example, this area supports demoiselle cranes, a species with poor maneuverability, poor frontal vision, and which flies in tight restrictive flocks. Their flight behavior also places them at risk as they make daily power line crossings between a roosting site and a foraging area. These flocks also contain young birds with less flight experience. All these factors increase risk. In contrast, this is not a breeding area, so courtship behavior is not a contributing factor. This image shows how various environmental factors impact risk. For example, this site is in a national park supporting many at-risk species, some which are nesting near power lines. At this location, cinereous vultures leave the nest each day to cross the power line to forage. Morning fog is also common. All these factors increase risk. In contrast, because it is a protected area, human disturbance is low, a positive environmental factor. Understanding transmission line collision risk factors are important in selecting a new line route. Sensitivity maps can be used to identify areas to avoid or where risk should be minimized. Such maps should focus on species historically susceptible to negative collision interactions, for example, birds with high wing loading flying in flocks. The conservation status of each species is also important because rare species should be afforded additional protection. Essential habitat areas, such as important birding areas and refuges, should be identified and mapped. Landscape features, such as water bodies, should be included as appropriate for the species of concern. Proposed power line routes should be mapped to identify potential conflict areas. Historical avian interaction locations and historical weather patterns, such as fog frequency, should also be included if available. These data should then be further vetted through field surveys by local avian experts. Experts can also contribute to the desktop review. Relative risk can then be assigned to the proposed corridors and a route selected. Focus should be on concentrations of at-risk species or areas with IUCN listed species If possible, the following locations should be identified. Foraging locations, including both natural and artificial. Breeding and dispersal areas. Local movement corridors. Migratory corridors and bottlenecks. Migratory stopover sites. Communal roosting and nesting sites. Wintering areas. There are a variety of data sets available to develop such maps. Some data are available at the global level, others at a regional level. For example, the Avian sensitivity tool for energy planning already has maps of avian sensitivity for power lines in India, Nepal, Thailand, and Vietnam. This table provides a resource for sites providing biological data on avian species, protected status, and in some cases, known migration and movement corridors. The IUCN website should be consulted for comprehensive information on the global extinction risk of birds. This site may also provide risk factors associated with species such as power line collisions. The site Protected Planet provides maps and data on protected areas. Such sites as eBird provide specific records of birds collected by citizen scientists, which is a useful way to confirm presence in an area. It is important to reiterate these sources of data should be used as a foundation which could then be reviewed and verified by local avian experts. Map data should be enhanced by field surveys and vetted by local avian experts. Various survey types may be useful in determining collision risk. Survey examples include abundance surveys and behavioral observations. After sensitivity maps are developed, various line routing options should be considered. One method is to collate facilities, placing lines parallel to each other. Placing lines parallel to each other reduces the number of avoidance maneuvers required of each bird. Another is to place lines near topographical features shielding the birds. Placing lines near topographical features parallel to the flight path reduces collision risk because the topography forces the birds to climb. Placing lines near existing human infrastructure, such as bridges, can also be used to reduce collision risk at water crossings. Power line design can be used to reduce both collision and nesting risk. Building lines in a horizontal configuration, as shown on the left, creates a situation where perpendicular bird flights encounter just two wire levels to cross. Using a vertical configuration, as shown on the right, utilizes less right-of-way, but creates a situation where perpendicular flights encounter four wire levels to cross, increasing risk. Configurations such as the bowl design compress circuit clearances. Because of the compact design, the conductors occupy a smaller portion of the airspace, which reduces the volume of hazardous airspace and may make the power lines more visible. They also use less right-of-way than other configurations. As previously mentioned, overhead ground wires place birds at greatest risk because they are smaller in diameter than the lower primary wires and thus more difficult for birds to see. Regarding mitigation, many transmission lines are fitted with either one or two overhead ground wires to protect the system from lightning. Thus, it is not desirable to remove overhead ground wires in high lightning areas because it jeopardizes reliability. Additionally, many modern overhead ground wires include fiber optics, so removing them would also impact data transfer capacity. We'll talk about how to mitigate overhead ground wires in subsequent slides. Undergrounding transmission lines is not typically a viable alternative to mitigate for collisions. Burying transmission lines has its own unique set of engineering and environmental challenges. The cable must have enough insulation to allow it to function within inches of the ground, and it must be able to effectively dissipate heat. Underground projects also require trenching, cable installation, backfilling, and then restoration. Undergrounding also requires large underground vaults at regular intervals for splicing. Costs for constructing underground transmission lines ranges from 4 to 14 times more expensive than overhead lines of the same voltage and the same distance. When mitigation is needed to address bird collisions, there are a variety of strategies to make power lines more visible to birds. The most common strategy is to mark power lines to make them easier to see. When marking power lines, the marking should be visible for the at-risk species. For areas where birds move in low light, luminescent and/or reflective markers should be selected, and markers with movement may also be desirable. Additionally, engineering considerations must be evaluated. This should include evaluating ice loading, wind loading, corona discharge if markers are going to be placed on energized lines, and vandalism potential. Marking is usually restricted to the overhead ground, which is the uppermost and smallest diameter wire. Primary wires are not typically marked, and marking wires above 115 kV can result in corona discharge concerns. When markers are placed on a single overhead ground wire, they are typically spaced 5 meters apart. When markers are placed on dual overhead ground wires, they are typically spaced 10 meters apart and staggered midway. Offsetting the markers still creates the appearance of 5-meter spacing for an approaching bird. When choosing a marker, installation considerations are important to review. For example, inaccessible locations may require installation using a drone or helicopter. Marker installation timing should be coordinated to avoid disturbing birds, and a utility should consider any unique requirements. For example, will an outage be required? Will there need to be road closures? Could weather impact the schedule? And most importantly, what are the safety concerns about a given installation method? Beyond line marking, there are other ways to make lines more visible to birds. One is to use ultraviolet light to mitigate nocturnal collisions. Many bird species see ultraviolet light, but humans do not. The use of UV has been shown to be effective in mitigating crane collisions. Habitat can also be altered to reduce collision risk. For example, altering the seasonal timing of creating bird attractants such as field burning or flooding can reduce incidents. This concludes the section on transmission lines and avian collision. To mitigate collisions, one must first understand risk, which includes transmission line factors, biology, and the environmental setting. For new projects, sensitivity maps should be developed to assist in routes with lower avian use to susceptible species. Along with routing considerations, the pole line design should consider flight risk. When marking is required, the appropriate unit should be selected for the species at risk and engineering considerations evaluated, including safety. Alternatives to marking, such as the use of ultraviolet light, are also available. This next section focuses on electrocution risk from distribution power lines, defined as lines with voltages below 60 kV, typically in the 15 kV range. Distribution power lines have tighter clearances than transmission lines because of their lower voltage. Distribution lines typically consist of a pylon supporting 3 energized phase wires on either pin or strain insulators, often on a crossarm. Common equipment includes transformers and switches connected by jumper wires. If adequate separation is not provided between different phases or between a phase and a grounded component, animals may become shocked or electrocuted. As with collisions, avian electrocutions with power lines are a global issue. Total bird numbers globally lost to power line electrocutions are unknown, but it is believed between 0.9 million and 11.6 million birds are killed annually in the United States. Electrocution risk is even higher in parts of the world where distribution systems are constructed with a preponderance of grounded contacts. Certain species are more susceptible to electrocution than others. Electrocution mortality constitutes a biologically significant cause of mortality to sensitive species, including the saker falcon. Methods for limiting power line electrocutions range from proactively avoiding exceptional habitat for sensitive and high-risk species, and also selecting designs with lower risk. Reactive measures include installing insulation and bird discouragers. Materials impact electrocution risk. For example, wood is a relatively good insulator, thus reducing phase-to-ground risk. Using grounded poles and crossarms significantly increases risk, shown in red. This is further compounded on more complex poles where bear jumpers are deployed, also shown in red. In order to address electrocution risk, you must determine the species at risk and its size, so proper clearances can be provided. For example, it is recommended to provide 150 centimeters of horizontal clearance and 100 centimeters of vertical clearance for poles located in golden eagle habitat. The best way to make new distribution power lines safe for birds is to build in the needed separation. Utilizing suspension insulators is also recommended. Existing lines can be fitted with a variety of insulating covers, making sure that they completely cover all the energized components. Products should be selected with superior ultraviolet resistance and insulating properties. IEEE 1656 is a good testing standard to review when considering products to purchase. Perching deterrents can be defeated and may be used to anchor nesting material and are thus the least preferred mitigation method. Nests on utility poles can result in outages, pole fires, along with dead or injured birds. The following recommendations apply to both transmission and distribution facilities. Structure design greatly influences nesting. For example, monopole transmission structures, as shown on the left, are difficult for birds to nest on. In contrast, lattice towers provide numerous nesting locations for a wide variety of bird species. Bird nests do not always need to be removed from utility structures. Allowing birds to safely nest on utility structures can also achieve important conservation goals. For example, in the Mongolian steppe, utility structures provide needed nesting locations for the endangered saker falcon. The location of a nest determines whether it should be removed or relocated. If a nest does not create any operational or maintenance issues, it should be left in place. Many birds, including raptors, reuse nests annually and defend their territory. It is best to leave such nests in place if possible. Nest management can be accomplished by installing platforms on existing structures in locations where nesting debris will not cause a conflict. Nests can also be relocated from structures to surrogate platforms. Biological support should be sought when managing nests to increase the likelihood of success. Stick deflectors, pole-top caps, and spikes can be used to discourage nesting in undesirable locations. Once mitigation strategies have been deployed, it is important to monitor them to ensure they work and that they are not creating any new engineering issues. This can include convenient sampling during routine power line inspections, structured surveys, or using automated monitoring such as deploying the bird strike indicator or animal activity monitor. The bird strike indicator, or BSI, is a remote sensor placed on a wire which automatically detects wire vibrations and then sends this information to a base station. These data can then be retrieved remotely. This is an Electric Power Research Institute technology. Thermal imaging video cameras can also be used, providing continuous monitoring. Sophisticated systems have algorithms to filter out clouds and wire vibration. Data can be remotely downloaded. Lastly, capacity building is needed for a project to be successful. It is important for the environmental team to understand engineering constraints of a new project. It is also important for the engineering team to understand possible biological consequences of a new project. Power line projects can be complex. There are a wide variety of topics engineers and biologists alike need to be aware of, as listed here. It is important to realize there may also be competing environmental concerns, which must be balanced against any avian risk. A variety of data sources to create sensitivity maps were provided in a previous slide along with web links. In addition, there are a variety of other guidelines available. Numerous references are available addressing both power line collisions and electrocutions, as shown in this slide. Some are global in nature, others specific to regions. This concludes the presentation on avian interactions with power infrastructure. The following are a series of quiz questions related to the topics presented. Thank you for your time and attention. Hopefully this presentation will aid you in power line design and routing in a way that makes your system more reliable while also saving birds. This presentation would not have been possible without the support of the United States Agency for International Development, the World Wildlife Fund, and the Center for Large Landscape Conservation. A wide variety of resources were used to develop this presentation, including information and research conducted by CGRAE, EEI, EDM, EPRI, IUCN, NABU, and the U.S. Fish and Wildlife Service. Thank you.